We start in a moment. I will share my my screen in a moment. So I want to start from the beginning our transmission issues. We were talking about various methods of data and signal transmission, and in I would say in passband, because our data, when we observe them, the frequency domain, they are located in so-called baseband. It means in the frequency band from 0 to given frequency. Because if you imagine, for example, that the high level it is 1 and low level of voltage it is 0, then if we have only ones, so we have continuous high level voltage, and so this is like a stable signal that doesn't change, and its frequency spectrum is just one sample in 0 frequency. So this is the best proof for that our natural code frequency spectrum is located in the baseband. And if we want to put the frequency, the spectrum of our data in a given location in the frequency band, we have to modulate the carrier function. And we said that the carrier function usually, well, not usually, always, it is a sinusoid, the simplest signal possible. However, in the modern systems like Wi-Fi, we have more of those carrier functions. But I will not go into details, but maybe I'll mention it later today. So the simplest method of of moving the frequency spectrum to a given band is to multiply a sinusoid function. Why? Well, I will not say physically why, but I will say mathematically how it may be explained. So the explanation is that amplitude modulation, it is multiplication of a signal by the carrier, and in the frequency domain we have to convolve those two spectra, one of my signal and the other of my carrier. And on the left hand side you can see just symbolically drawn spectrum and of a signal and spectrum of a cosine function, and if we convolve those two we will get our spectrum moved to the frequency indicated by our carrier. Somebody asked me after a last lecture about the convolution, so maybe it's not so obvious for you. Maybe next time when we meet, but next time we will meet again in the over the internet. But I recommend you just to have a look into this image, and if you spend some time and if you look at this formula and you look for the the parameter t that changes from minus infinity to plus infinity, you'll probably understand what does it mean. And our case is very simple, because instead of this rectangular function we have only Dirac delta in this case of amplitude modulation. And if we want to recover our signal on the receiver side, there are some other methods too, but the most used is coherent demodulation, when you again multiply your modulated signal that is coming from the transmitter by the same cosine function. The same cosine function, and then what you get, you have to convolve again this moved spectrum by the spectrum of a cosine function, and if you do that, you get the movement of those spectra. One is moving to the frequency being twice as big as the carrier function, and the other is moved to zero frequency. And the same is happening on the left hand side from the minus part of frequency. So you get the spectrum near zero frequency. How it works for two cosine functions, I have been showing you here. So the convolution is related to the movement of one signal from minus infinity to plus infinity, and this moving function for each location has to be multiplied by the other function. And when this is value different from zero, well, your result is different from zero. So you put this impulse in the place where zero of this first function was moved. So I cannot draw here, but if you take this spectrum and you put it here, then in the middle is the zero of the axis moved to this place. That's why you have the impulse in placed in -7 kilohertz. And also we were talking about the possibility of multi-value modulation that gives the possibility of increasing the bit rate without increasing uh, modulation rate. So for example, here you have 4 different phases. So one phase uh, is responsible for 2 beats. Yeah? So you have the carrier, and suddenly this carrier changes its phase uh, of 270 degrees. So you know that another combination of bits is coming, and since we have 4 different phases, we we can code here 2 bits. I want to draw your attention to the fact, I didn't say that last time, but look, here you can see the symbol delta F. That means that we have the difference of phase. So it is not like we have 4 different phases and we just switch between those phases, but the system somehow knows what was the initial phase of the previous chunk and changes the phase of a given number of degrees. So it is more often this differential. In fact, we are saying that this is a differential modulation. Okay, so here you have an example of 8 values modulations, where you have 8 phase shifting, and since you have 8 combinations, you can code 3 bits. That's why the frequency, the bit rate is 3 times as big as the modulation rate. And that's why also we have different units for bit rate, which is bits per second, or kilobits per second, or megabits per second, and um, not so often used nowadays, bauds. One baud, it is one change of the carrier. So this is, one one phase related to this part of the signal, and here we have 3 bits. So we have a PSK, which is phase shift keying. We have FS key. You can see here 3 different values. So it's frequency shift keying. So the parameter that is changed for carrying the information about bits is frequency. We have amplitude shift keying, which I started to discover at the beginning, and we have also a combination of AS key and PS key. Now frequency modulation, a small repetition. So frequency modulation has much more complicated spectrum, but the good thing is that it is less sensitive for various noises and distortions. Why? Because when analyzing the receiver, the signal got by the receiver, we don't pay attention to the amplitude. We rather pay attention for the frequency of the signal. That's why the amplitude of the modulated signal that might be disturbed by various clicks, noises, and so on and so forth, uh, are not are not taken into account on the receiver side. This is in the contrary to amplitude modulation, where we have the exact same spectrum as the original signal uh, that caught all those distortions. And when we recover the spectrum in baseband, we have the same distortions in our signal. And I told you that in the past, when we had analog television, the image information was coded by amplitude modulation, uh, and voice, sound, frequency modulation. And still, we prefer to listen to the radio. If we have an analog radio, we listen to FMs, not AMs. So this example here has shown the idea of frequency modulation in comparison with amplitude modulation. So here the slow sinusoid modulates the carrier, faster sinusoids. So here you can see the changing amplitude of the signal. And here you can see the frequency changed by the sinusoid. So this is nonlinear transformation of the signal. That's why the spectrum is very complicated. Someone could think that if we deal with two sinusoid, it will be as simple as it was a few slides as it was here. But no, since we modulate the frequency, in each moment we have completely different signal. So, but on the other hand, those changes are periodical. So we have to see some since we have the periodicity in the signal, we must have the discrete spectrum, and we have to have some, let's say, harmonics, and we have them, but there are plenty of them. Yeah, and the highest value is the carrier frequency, and I pay your attention that in fact it is a imaginary frequency, a carrier frequency, because in fact we do not have a stable moment that we could observe such a frequency. So let's imagine that this sinusoid has let's say 100 hertz and the other has 1000 hertz. So this carrier will be the average. It means it will be 1100 divided by 2, so it'll be 550 hertz here. And we will see that. Yeah, we will see that that value, despite the fact that it is unexistent here. And those other samples are in the location equal to, in our example, 100 hertz. So it means they are in such a distance like the frequency of this modulating signal is. And what is very, very interesting, the similar spectrum, we may observe if the modulating function is in the shape of a rectangular. How can we how can we explain that? Well, the explanation is that the rectangular function has some harmonics that are that have frequency being the multiplication of a fundamental frequency. And the fundamental frequency will have the shape of such a sinusoid. And if those sinusoids, if those samples are in the distance being the multiplication of this frequency, so if we have another harmonics of the rectangular function, they will be placed in the exactly same places in the spectrum. But of course, the amplitude will be different. That's why when we have such a situation that we have a rectangular function that modulates or keys the frequency of a sinusoid, we get the spectrum very similar to previous one, also very complicated, and that has this imaginative carrier function, and the samples being in the distance of the frequency of this square function. Yeah, of the square quantity. Of course, we have to pay attention and be aware of the fact that this is the simplest possible representation of frequency shift keying when the modulating function is periodical. So if we imagine the sequence of data that would be transmitted, it would be 0, 1, 0, 1, 0, 1. Why we are not showing other possible cases? Well, first of all, they would be infinite number of this combination. The second one is that the spectrum would be more complicated. For example, if you take the sequence 0, 0, 1, 0, 0, 1, so our carrier function, this multiplicative imaginative carrier function, would not be in the same place because there are more, if I can say like that, of one frequency than the other. So 2/3 would be of one frequency and 1/3 would be of the other frequency. That's why the carrier would be moved into the frequency that is more represented in the signal. But if we can imagine completely free data, completely random data, then our spectrum changing in each moment can be averaged, and then we are saying that we have the spectral density, and that's why we can draw the spectrum as an analog line, not discrete. Yeah? So such a discrete function, such a discrete signal, we will get only in the case when our data repeat periodically. But if our data are completely random, then in each moment we have a different different spectrum, but we can average this spectrum and show how, it may be said, how often a given um, a given frequency is represented by the signal. And this is what I was showing you last time, that here we have uh, the examples of spectral density. It means, well, I had in the past, when I had such a subject data transmission, I had a very good program simulating data, uh, random data, and then we could calculate the average spectrum. And then it was very clear that you don't have special harmonics. Sometimes you could see some values that are bigger, but it was a continuous function, of course not so smooth as here, because it's an ideal situation when we watch the data from minus infinity to infinity. When I had a simulation, I could use, well, let's say 64,000 beats, for example. It was maximum, so it was not so smooth, but the shape could be seen. And then maybe I could persuade some students that it is really like that. But if you have a given a sequence of periodical data, you get this very, very clear, uh, very clear peaks or impulses in the frequency domain. Okay, so let's have a look into this table to understand what's going on. So first of all, here you have the modulation frequency, which is the inverse of the bit length. Here you have this frequency, repeating frequency of the sequence of 2 bits, 0 and 1. So we call it F frequency, but in fact it is twice smaller than modulation frequency, or modulation rate, maybe it will be better said. Then we have this carrier, which is the average of two frequencies for 1 and for 0. And as I said before, if we had, for example, 2 zeros, we would have more of this lower frequency. So for example, it is 100 and this is 200. So, well, and this may be 100 and, well, okay, 100 hertz and 200 hertz, so it will be twice 100, it's 200, and plus 100, which is 200, is 400. It would be divided by 3. No, not by 3. By 3? By 3, yes, by 3. And we would have the carrier frequency. So this frequency difference is important to calculate the modulation index. This modulation index is the most important parameter in frequency modulation or in frequency keying. And it depends on the difference between those two frequencies for 1 and for 0. And of course, the frequency of the modulation or modulation rate. So in fact, this modulation index is calculated as two values of frequency difference divided by modulation frequency. So for example, in my example, when I had said that this is the frequency of 100, this is the frequency of 200, so the difference is 100. And if we had the frequency, the bit rate of 100 bits per second, we would have modulation index equal to 1. Equal to 1. But if we had, for example, faster modulation, like 500 bits per second, we would have the modulation index 1/5. Yeah, 1/5. And look what would happen if it is if it is 100 hertz and we take into 100 hertz, so it is 1/10, 1/100th of a second. And if we have 100 beats per second, our beat would be as long as one period here of this sinusoid. But if we have the bit rate of 500 beats per second, we would have a small part of this frequency only here. Is it possible? Well, it's very, very difficult to be demodulated later on. So we cannot make as small this beta parameter as we wish, but we would like, it was my question last time, what do you think for data transmission, what kind of beta would be the best? And the answer was, the smaller it is, the better. Yeah, because we have the spectrum, all the energy of the signal concentrated around the carrier frequency, and it's very narrow. And in case when we have a big value of beta, it is not so narrow, and the maximum of energy are near the end of our band, and it may be distorted by filters. But on the other hand, when we have a radio transmission of analogous signal, like for example in transmitting music, if we have a big beta parameter modulation index, then it'll be more easy to represent by frequency changes, to represent the changes of the amplitude of the signal by the frequency. Because what kind of conversion we have in frequency domain? The amplitude of the signal is converted into the frequency of modulated signal. So I can be very, very precise in representing amplitude of an original signal by frequency changes. So when you see the speech signal, for example, you can see that you have the high values, but you know you have all possible values of amplitude. And all of them should be very well represented by frequency changes in frequency modulation. And that's why in the radio, for example, in radio transmission, beta indexes or indices are very big. For example, they are equal to 20. So So it's the spectrum is really very, very wide. In the middle, there are no um, much energy. At the end of the band, there are more, but uh, the good thing is that we can represent amplitude of the signal very, very well and precisely. And in the data transmission, we have only amplitudes of 1 and 0 or 1 or minus 1. That's why we do not need to be so precise uh, with the amplitude representation. We have only to decode 1 and 0, 1 and 0. That's why the other reason why we don't need such a big modulation index. And I gave you a kind of a homework to to find out what is the modulation index in Bluetooth. Did you find it? Somebody remembered to check what is the modulation index for in Bluetooth? If not, I'll give you another. I'll pass the same homework for the next time. Check how Bluetooth works and be sure that it is a kind of a frequency modulation, and try to find out how big the modulation index is. Yeah? And then I must say that most of Wi-Fi systems rely on frequency modulation. Other modulations are used in industrial applications, in sensor networks, and so on and so forth. I will mention it later. What we had here, yeah. So if you have a look into ASK and FSK, you could see that the spectrum is different. Well, now a small comparison, because we have another method of data modulation, and this is rather funny because up to now we tried to make our spectrum as narrow as possible in order not to use too many bandwidth, which is very, very valuable nowadays. But there are systems where we use a very, very wide bandwidth for transmission. And you have here the comparison. Maybe it's a very good example to um, to order your information. So um, our data are in the baseband, and it looks like that. Maximum frequency is B. Our amplitude modulation moves the whole spectrum to the frequency of the carrier. And the drawback is that our spectrum is twice as wide as the original. Of course, as I said last time, we have methods to diminish the energy of one of the bands, but in general, it is twice as wide as our baseband frequency. If it comes to the frequency domain, we have even wider band occupied by our modulated signal. And you could see here that it is from 2B to 20B. Well, maybe I come back to this to this image, because you see this difference between those peaks. It's like frequency f. It means it's 1 divided by 2b. So if we have such an example like here, this one, look, this is change in the units in the axis, because we have here delta f divided by modulation rate. So if we have 1, it means that that here is our spectrum has a very, very small value, and most energy is in this place. So probably the frequency of the signal is it's somewhere here, yeah. So so it is related. Okay, so this modulation frequency is here, and we may say that it is one frequent one maybe the width of a band of our modulating signal. So here the width will be 2 values of our frequency of the signal. But in this case, for example, we have 2 values, and if our beta would be higher, we would have here more values. That's why here in this case, you can see that you have the width of the band from 2b up to 20b. If our modulation index is equal to 20, we would have the band occupied by the modulated signal equal to 20b. But there are cases when we have this width much bigger than 100, and this is so-called spread spectrum systems, where the spectrum is really spread by the very big range of frequencies. One more thing I would like to show you, that in each case when the frequency then the band is bigger, the amplitude of the signal is smaller. So if you calculated the surface below this function, or this function, and this function, and this function, it would be always the same. So it's one important thing. Then when we will be talking about the spectrum, we have to remember that the energy of the signal is very, very small. But before we go into spread spectrum systems, I would like to pay your attention to the fact that if we want to transmit data in the baseband, we could imagine that we have only the situation when we have direct transformation of our bits into high voltage and low voltage, and the 1 it is high voltage and 0 it is low voltage. And here NRZ means non-return to 0. So sometimes it is called natural modulation, NRZ, which means non-return to 0. Here you can see the differential NRZ. It means that when you have change from 1 to 0, you do not have the change of the level of the signal, but when you have ones, yeah, so when you have the change to 1, doesn't matter if from 1 or if from 2, you have the change of the level. So this is the idea of differential modulation. So usually when you have 0, you don't have the change of level or phase or whatever it is, and when you have the change, the 1, then you have the change of the level. So here you have the change from 0 to 1. That's why there is a change of level. From 1 to 1, so the next bit is 1, that you have the change here to 1. And then you have 0, so no change, no change, no change. Then again 0 to 1, this is the change. Then again from 1 to 1, so our next bit is 1, so we have a change. 1 to 0, no change, and so on and so forth. Yeah. Here you see this is RZ. It means that it is return to 0. And I want to pay your attention because it is one of the most used codes. For example, in our USB, we have such a return to 0 codes. Why it is like that? Because it is in fact it is the transmission of a clock, of an internal clock. So the clock looks like that, yeah, that in one bit you have 2 changes of level. But it is not so good, because when you have ones, you have the impulses, and when you have 0, nothing is happening. So when, for example, you have a long time of 0, then your system does not have any possibility to synchronize. It is the same with those 2 codes, NRZ and NRZ. That's why sometimes we have a bipolar return to 0. And it means that when we have ones transmitted, we have high voltage, and when we have 0, we have minus negative value of our voltage. So it's easier. So we call it bipolar return to 0 code. There were a lot of very interesting codes that were used, for example, at the beginning of electronic telephone switch centrals. Then we had so-called AMI codes, also return to 0, and you may see that the impulses were uh, every even impulse was positive, and odd impulse were uh, negative, or vice versa, And I don't have here another example. For example, another code would be HDB3, and the system there was more complicated. It was that if you have three zeros, you may code them as a zero. But if you have more than three zeros, you have to input an additional impulse. So it was rather complicated to generate and to a bit to understand. But we had an example of such a generator built by students, and we could show how it works. So this slide is only to show you that even if in the baseband, the situation is not so clear that we have only one frequency. I must say, that's a pity. I don't here have, I have to put it, because we have very, very popular so-called Manchester code. Now I can see that I didn't put it here. Just I wanted only to show that such diversity exists. But I should have mentioned about the Manchester code, because Manchester code is one of the most used, and if you have an imagination, you may imagine that it was coded like that, one value was like a clock, and the other value, it was like here, maybe here I should show that here we have a clock, and in the moment when you have a change from 0 to 1, the clock changes its phase. So if we had here small 1 and small 0 and small 1 and small 0, so in the moment of this change, we have again 0 and 1. And we have again a change. So we have twice as long 1, and then again we have 1 0 1 0, and so on and so forth. So the change of data value was coded as a change of frequency, sorry, as a change of phase of our clock, and this is called Manchester. So again, a homework for you to check what is Manchester code, just Wikipedia or something like that. So mathematically it's quite easy, because you could imagine that as a sum modulo 2 sum of the signal of my data and the signal of my clock, internal clock. But of course, practically, it's not so good, because you don't have exact, you have the possibilities of distortion, maybe I'll say it like that. Okay, so another homework. First homework was to find out what is the frequency of what is the modulation impulse of not my, of the Bluetooth. And the second homework is what Manchester code is. Good. And now we are moving to spread spectrum systems. So we are moving to this last example here. How it works. First of all, I have to say that it was discovered and used in military applications. Why? Because if we can wider very much the spectrum of our signal, and in the meantime we diminish the energy, we can hide the information in the noise. because the information itself has a character of a noise. Why? Now I will explain it. I will explain it on the very easy example, but in fact, in reality, it is much more complicated. Imagine that this is our data. Yeah? This is our data. We have 1 and we have 0, and we have a bipolar representation of data. And now what we do, we have a so-called spreading code. And spreading code is a sequence of zeros and ones of a very special characteristics, that it is a kind of a pseudo-random sequence of data that may be represented by a generative formula. And if you multiply this and if you send it, it may have a character of a noisy sequence. Of course, it is not so obvious when this spreading code is very short. I don't want uh, to introduce here a lot of theory about that, but the only thing is that we can generate such a sequence by kind of by kind of a formula represented by, oh my god, how it is called in English, by polynomial or polynomial polynomial formula. And in this case, when we have seven bits here, it would be generated by the polynomial of the degree equal to 3. And if we have the polynomial um, of the degree of 4, we would have 15 beats. If 5, it would be 31. 6, it would be 63. 7, it would be 127, and much more. So you can see that it is 2 to the degree 2, 4, 5, 6, and so on and so forth. So we are able to generate such code that are pseudo-random, and if the receiver knows this sequence, it means if the receiver knows this polynomial, it is easy for the receiver to change the data obtained into original data. So what we do, we just take our data and we multiply it by this pseudo-random formula. So if we have here 1 and here we have 0, and we have this formula that repeats periodically, then here we have 0, 0, 1, 1, 1, 0, and just a moment. Sorry. So our formula is 0, 0, 3 ones, it is 5, 0, it is 6, and 1, it is 7. Yeah. So in this case, we have 0, 0, 1, 1, 1, 0, 1. And now the inverse of this bit would be 1, 1, 0, 0, 0, 1, 0. Yeah. And this is the signal we transmit. Yeah. And of course, we don't transmit it in the baseband. What we can see that the bit here is 7 times shorter than original bit. So we may imagine that our spectrum, modulated spectrum, will be 7 times as wide as the original one. If we have, for example, the spreading code length 127, then we may imagine that our spectrum, modulated spectrum, will be 127 times wider than the original. And of course, the energy will be much smaller. And if this signal has is a pseudo-random, there are no periods within this 107 and 27 beats, then we uh, we do not see there any periodicity. It's pseudo-random. It's like a noise. So when we imagine that the energy is much, much, much smaller, then non for the observer, it'll be a kind of a noise. Yeah. So for military applications, it was great. So some time ago, it was transferred um, to the civil applications, and that's why we have Wi-Fi and things like that. Yeah. But of course, we do not transmit data in the baseband, but we have to use one of the modulations of a carrier we know to put it somewhere into the frequency bands, somewhere very high. So the carrier is, as usual, sinusoid, and here we have BPSK, so modulation, bipolar phase modulation that modulates us. This is this one beat, yeah. So it looks like that. And imagine if the receiver part has the same sequence of spreading code, and when the receiver part multiplies the data by the same um by the same spreading code, you can check that you would get exactly the same signal as we have here. So there are two conditions uh, to decode this data. One, to have a spreading code, and the second, to be able to synchronize the data. Because even if you have the spreading code, but you will not start when the bit starts, you may have some distortions. But still, in the receiver side, there are some methods that even if there are some distortions, you can get the information. Well, what I would like to say that the direct spectrum, it's the simplest method of spreading a spectrum. What we have in our Wi-Fi, if if it is a so-called frequency hop spread spectrum, what it means? It means that the spreading code is applied to change the carrier of a signal. That's why our frequency modulation is not now like having only one carrier, but it has a lot of carriers. For example, in this case, it would have 7 different carriers. Uh, and of course, the signal would be, in various bands related to those 7 carriers. If we have a longer spreading code, we would have even more uh, carriers. So each bit will be in a different carrier. Or uh, each bit packet will be in a different carrier. There are some differences in frequency hop spread spectrum. It's a little bit more complicated. Um, I didn't want to put it here um, into our lecture, but maybe I should have done that. Um, to not to show you on the picture, but on the other hand, I wouldn't like you to learn too much, so this is the material that will be used at on the exam. So I would like you to be aware that we have a frequency hop spectrum, spread spectrum, and it would be good as a third task for your homework to check Wikipedia or anywhere what is frequency hop spread spectrum. We have we have also uh, mm, time hop spread spectrum. So this is another method, but I really wouldn't like to spend time on that. You can check it. But I would like to mention a very, very interesting um, uh, method of spreading spectrum, which is called chirp modulation. Um, I didn't mention that until the moment when the LoRa systems were introduced in the Internet of Things applications, and the LoRa uses chirp modulation. What is chirp? In Polish it is świergot, modulacja świergotowa. One of the students asked me why it is called świergotowe, why it is called chirp. What is a chirp? Chirp, when you can see here, maybe it's not very exactly, but probably I could in when we will be in the class, I will make you listen to that. But you can see here that this is a sinusoid, yeah? But the sinusoid has a linear increasing frequency, linear increasing frequency, and of course mm, it takes some time for the chirp. Yeah. So if you watch the spectrum, averaged spectrum of this chirp, you can see that the frequency spans from the lowest frequency to the highest frequency, and it might be, well, no matter how big band occupied. Of course, if you look at the spectrogram, probably you know what spectrogram is, that we observe frame by frame our signal, and those changes are plotted in time. So we would have the frequency increasing from the lowest one to the highest one. But when we average that and we calculate the spectrum, we can see that this is that it occupies a certain band. That's why um, chirp modulation is one uh, of spread spectrum methods. Yeah? And how it works. So this is our chirp, and according to the spreading function, we can cut this chirp into pieces, and in each time of one beat, you may have various combinations of representing the parts of this chirp. Here you have only four combinations. So, or it everything goes linearly, or it starts earlier, and then you have from the smallest frequency to the highest. Here you have divided 2 by 2, and here is first the highest frequency, then the lowest frequencies. And you may imagine that we have in other systems, we may have more such a cutting chunks or chips as we use it. So for example, we may have 127 chips, various chips within one bit. And this is why we may say that this is a spread spectrum, and the pseudo noise is applied to the different cutting of my frequency changes. Yeah, and here I generated it in Audacity to show you how this frequency change in spectrogram looks like. So such symbols um, are emitted when we want to modulate our data. And here you have um, the real signal when you have for example, at the beginning, you have a synchronized version for synchronization, and then higher here you have the real data sent in a given band. Yeah, and it look so. This is the frequency change, and the time is this case. It is here growing time. And at the end, I would like to come to the Earth and a small table where you can see the comparison of transmission parameters of various wireless networks, of course used mainly for Internet of Things. Yeah. Mm. And what we can see here, well, you can see the system which is called ZigBee, wireless MBUS, and ocean. Oh, sorry, M MBUS in ocean, LoRa, and Bluetooth low energy, and also Wi-Fi high and low, which probably it's introduced already in practice, but in the moment I put here this table, it was only in plans. So you can see here the names of the standards and the frequency band where this signal is located. So it is or 2.4 gigahertz, like in the case of ZigBee or Bluetooth low energy, or 868 megahertz. Uh, um, another line, it is a band occupied. So in the case of ZigBee, you have 16 channels for 5 megahertz. So theoretically, modulation rate here would be 5 megabaud. In wireless MBUS, the frequency is or 600 or 500 kilohertz. An ocean is 280 kilohertz. In LoRa, you have three various possibilities: 125, 250, and 500 kilohertz. And you have usually two channels. One is for sending the information, and the other is for receiving information. And for receiving information, usually it is uh, much lower bit rate. And in Bluetooth, you have 40 times 2 megahertz. And Wi-Fi high, low will have 1 megahertz or 2 megahertz or 4, 8, and even 16. Look for the distance. So if for ZigBee it is 10 to 100 meters, you can see that it may be used uh, only for specific applications, and those specific applications are in sensor networks, for example. In wireless MBUS on the open air, it is until 1 kilometer. And of course, it is very important if it is an open space or somewhere in the city, because in the city there are so many distortions that this distance is much smaller. In ocean, it is 30 meters in buildings and 300 meters in open air. LoRa from 2 to 5 kilometers in urban applications and 15 kilometers in suburban. We have here in our group Dr. Novak, who has introduced LoRa some time ago and has plenty of very interesting diploma works related to LoRa applications in real circumstances. So, unfortunately, for example, this year, I don't know why, you know, it's a digression. Today I didn't make digressions at all, but this is one digression. Usually, in the second level, he has plenty of students that want to write his thesis with him. In this year, he has already 6 of them. A full group of 4 people came to write thesis and to do experiments with the LoRa and other Internet of Things applications. So he has already 6 of them, and the themes were not given yet. Uh, Topics of the master thesis, but I don't know why this year he doesn't have students for writing engineer project, preparing engineer project. It's really very, very strange, because usually he's very, very popular. So if there is somebody who is interested in those things, I can recommend it to contact Dr. Novak for preparing the engineer project. Yes, so Bluetooth, because, well, beacons and things like that, and computers and sending images and things like that via our smartphones. So, um, so this is the distance. And Wi-Fi, halo, it's 30 to 100 meters. Transmission rate, not so high, you can see. ZigBee 250 kilobits per second. Wireless MBUS 4.8 kilobits per second. Well, it depends on the system, yeah. And Ocean 125 kilobits per second. LoRa from 300 to 50 kilobits, 300 bits per second to 50 kilobits per second. Bluetooth 1 megabit per second. Hello, 150 bits per second or higher. Well, today what is very important, it's power. Yeah. So ZigBee is 1 milliwatt. So it's a green power. So it's really great, because when we have to decide what kind of system to use, the power consumption is a very, very important parameter. LoRa, it's less than 10 milliwatts. And Wi-Fi Halo, it's 6 milliwatts. It's a really rather small value. Also, the sensitivity. I have told you at the beginning of our meeting that when we talk about signals, we do not use linear units. We use decibels. And decibels, it's a logarithmic unit. You have to have the value, reference value, and you compare, you divide your measurement by this reference value, you calculate the logarithm, and then you multiply it by 20 or by 10. It depends if it is power or energy or amplitude. If it is amplitude, you multiply by 20, and if it is power or energy, you multiply it by 10. And you can see here dBm. So dB stands for decibels, and M, well, it is one of the units you may have here. M, U, and other letters. M means that the reference value is 1 milliwatt. 1 milliwatt. Yeah. Okay. So you can see how it looks like. So the sensitivity for LoRa is very, very high. And modulation. Oh, this is for the end of our meeting. 2 minutes. So you have QPSK, what is quarter phase shift keying. It means that there are 4 values of phase. This O, well, it's a kind of a version of QPSK. QPSK, it's 4 values for phase shift. BPSK, it is bipolar phase shift keying. It means that we have 2 values of phase. And DSSS, it means that it is direct spread spectrum system. Wireless M-Bus, you have the Manchester code in the baseband that I said, and 2FSK. It means that there are 2 carriers in frequency shift keying. An ocean is amplitude shift keying. LoRa is chirp spread spectrum. And Bluetooth, oh my God, already you have a homework, but you can see here GFSK. I told you that it is frequency shift keying, but this G stands for the formation of an impulse of data, which is not square, but which is Gaussian shape. And Hi-Fi Halo, this is, so you know, higher knowledge, OFDM. OFDM is a frequency modulation, but you may find there 500 carriers, and it's really rather complicated. Uh, it stands for orthogonal frequency frequency. Oh, D, I forgot for D. Modulation. And BPSK or QPSK. Yeah, so those two. And QAM, it's quadrature amplitude modulation. It means that this is again amplitude modulation, amplitude and phase modulation that has 16 on 256 up to 256 different values. So if I had uh, to present everything, all the methods that are used, it would be the whole course. But you know, if you are interested, you just may um, you might find for yourself the information. Yeah. So that's it for today. Thank you for coming. No time for questions and answers. Um, so uh, maybe next time you have plenty of time. Uh, I just sit down. Um, yeah, and I have two final steps for letting you use our e-course. So during this 2 weeks time, you may have a look into the notes and prepare to question and answer session next time. So thank you very much.